Hey guys, today I want to take you through a couple more examples with trig identities, give you a couple more tips, and just remember as we're proving, we always want to have our fundamental trig identity sheet in front of us with the additional ones that I asked you to add to that sheet. These are just rearranged versions of the trig identities above. So try out this warm-up question and take a second to pause the video, and then we'll come back and do it together. So now that you've had a second to try this on your own, we're going to make sure that we set up the proof in proper format. So copying out what's on the left side of the equal sign and the right side of the equal sign just to start here. And our next biggest tip was, after we've kind of set everything up properly, we are aiming to get everything in terms of sine and cosine. So I think we're pretty good on that, except we do have a tan x. So going back to our identity sheet here, it looks like tan x is equal to sine x over cos x. So we can simply replace tan x with that in our proof. All right, so we're going to plug that in here. And then I'm just going to simplify this fraction. Think of this as sine x over 1. We're going to multiply the top and multiply the bottom. Remember, you don't need a common denominator when you're multiplying fractions, only when you're adding or subtracting fractions. Which brings us to our next step here. So typically when we're adding or subtracting two fractions like we are now, we would find a common denominator and put these together. Now, this one already has a common denominator, so we can simply put the fraction together. And I'm also always looking here to see where I'm headed. So I can see on the left side that I want to end up with just a single cos x. So that tells me that I'm probably going to have to do something with this 1 minus sine squared x to be able to cancel out with this cos x on the bottom. So if we look back at our trig identity sheet, should notice here that we do have an identity, a rearranged Pythagorean identity that says 1 minus sine squared x is actually equal to cos x. So we're actually just going to replace 1 minus sine squared x with cos squared x. And now I have cos squared x divided by cosine, which means that I can cancel out 1 from each of these, and I'll simply be left with cos x, which is what we have on the left side. So now, just to finish up our proof, we typically put left side equals right side, and a lot of math proofs we kind of end with a little square or the abbreviation QED for that Latin phrase that means which had to be demonstrated. So there's our proof. Okay, so our first video, we had some tips and tricks. One little extra note that I did want to add on as well, which you may see in your trig identity travels, is this. So let's say I have something like this, sine plus cos x squared. Now, one really important thing here, guys, and this is like a major math crime, is that people tend, when they're working with trig identities or something new, they kind of like let all the math rules fly out the window. And some of you may be tempted to say that this is equal to sine squared x plus cos squared x. This is actually not true. So we definitely don't want to say that. What we can do if we want to express this in a different way to be able to work with it is we can actually FOIL this expression out. So this is actually equal to sine x plus cos x times sine x plus cos x, which means that we'll simply FOIL, doing first, outside, inside, last, and this is what we'll get. Okay, and then we can simplify this to sine squared x plus 2 sine x cos x plus cos squared x. So we can actually do this both ways. If you see this in your trig identity and it's not quite working for you and you need to express it in a different way, you can actually FOIL it out to this. And if you see this in your trig identity at the bottom, you can actually factor it back into this form. So this actually works both ways. It depends what our trig identity looks like. for how we might want to use that. Also, you may see that we have a sine squared plus a cos squared, which is actually equal to 1. So what we could do is even take this a step further, and we could say this is equal to 1 plus 2 sine x cos x. Okay, so either this way or this way, we can factor or FOIL. So I guess we would say going this way would be to factor a perfect square trinomial, and going this way would be we would be foiling a perfect square trinomial. Okay, so take a look, keep a lookout for those on your worksheets. I think number 6 on our worksheet requires us to FOIL out something like this. All right, let's take a look at a few more examples. So setup is all up to you here. Just make sure that you're separating out between left side and right side. We'll copy out each side here. And I want you to think about how you might start this one. Okay, if we look at our trig identity sheet, we have a tan squared and a sine squared here. So let's take a look. So on one hand, we have tan equals sine over cos, and we talked about how we can square each side of that identity. So tan squared equals sine squared over cos squared. We also have this identity here. And typically we've talked about how like 90 to 95% of the time the right move is going to be to put everything in terms of sine and cosine. But if I rearrange this formula, I see that tan squared x is actually equal to secant squared x minus 1 if we move that 1 over. And that could be a potential way that I could go with this as well. So that's definitely an option here. There are many ways to prove something, or maybe I should say multiple ways that you can prove something that may be different from the way that somebody else does it, but still correct. So why don't we try this out? We're not quite used to doing something like this, but we'll try and see what happens if we put this in terms of secant squared x minus 1. Okay, maybe we'll try that over on the right side here. Okay, now the cool thing about this is that all of a sudden, now that I've done this, I have something minus something, and that's kind of what we have over here on the left-hand side. So remember that secant squared is actually 1 over cosine. So when I bring this, actually maybe we'll do that first. So if it's secant squared, it's 1 over cos squared. And then I'm actually going to distribute this sine squared into each side here. And what you'll notice here is that we get sine squared x over cos squared x minus sine squared. And I have the minus sine squared part. I'm just looking for the tan squared part. And if I kind of look at this, I see that the tan squared is in there. Tan squared is equal to sine squared over cos squared. So we can simply replace this with tan squared x. Okay, so that's one scenario where I could potentially use a different identity first, but you will notice that after that I did turn everything in terms of sine and cosine. You could have also replaced this with sine squared over cos squared to get to that point right there. So lots of different ways that you can do this. It definitely would still work if you chose to go the route right at the beginning where you turn everything in terms of sine and cosine. Okay, let's try another one. So you're going to set up left side, right side, and you're going to copy the left side of the equal sign and copy the right side of the equal sign. Okay, one really quick thing that I can do here is I know that secant is the reciprocal of cosine, so I might just plug in the reciprocal of cosine here. And probably the best way that we can go, there's not many other routes that we can take here because I don't really have any squareds, so I can't really use these Pythagorean identities anymore, but I can use that tan squared is equal to, or sorry, tan is equal to sine over cosine. So I think that's the route we're going to have to take here. And I guess we don't really need brackets around it. Okay. Now, one tip and trick that we talked about in our intro to trig identities lesson is that when we have two fractions being added or subtracted, it's great to get a common denominator and put them together. So that's what we're going to do. This side needs a cos x on top and bottom. And this side's going to need that 1 plus sign on top and bottom. Okay, let's merge these together in one fraction. Okay, over here, I think we're just going to put that as cos squared x. And then we've got cos x times 1 plus sine x. Okay, now you may be tempted at this point to want to cancel these guys. However, we can't do that. If we think back to our rational expressions knowledge, when I have a plus in here, I can't cancel separate pieces out. It needs to be all multiplication happening on top and bottom in order for us to do that. So we can't do that quite yet. When we can't do that, a good idea usually is to expand and simplify the numerator. Now the denominator is kind of already fully factored, so there's probably not much that we'll be able to do there. So let's try expanding the numerator first. Okay, again, I'm also looking at where I'm headed here. I'm looking for just 1 over cos x to remain. So I do have that piece. So hopefully I'll be able to kind of cancel out the top and the bottom so that I can get 1 over cos x remaining. So where can we go from here? Well, I'm noticing that I have a sine squared x plus cos squared x here, which is actually a Pythagorean identity. It's actually equal to 1. So I'm going to replace that with 1. Maybe we'll just go on to the next little page here. Sorry, one sec. All right, made some more space here. So we're going to replace that with 1. And then I think the final question here is sine x plus 1 the same as 1 plus sine x? So is 7 plus 1 the same thing as 1 plus 7? I think that's true. So if we consider this kind of like a group here, I can cancel this and this. Now remember, cosine is in the denominator, so what's left in the numerator is actually just 1 here. So we've actually got 1 over cos x remaining, which is equal to our right side. So we are good to go with our proof. So finish your proof off, left side equals right side with a little box. All right, yesterday I gave you a little tip, and that tip was when you see exponents that are not 2's, sometimes it's helpful to use power rule. So we're just going to set up our left side and right side. This is a new little symbol. It's called alpha. You may have seen it in your trig travels before. If you want, you can replace them with x's or thetas, whatever you feel comfortable with. Okay, so there's a couple ways that we can go here. I can start working on the right side, or I can try the left side out. So both ways should work. But we did talk about yesterday, when we see something like sine to the exponent 6, I can actually simply just say this is kind of like sine squared cubed, right? It's like power rule. A power on a power means that you multiply the powers. So this is just an equivalent expression for that. And I know if I'm headed for 1 minus cos squared x and sine x, those look like a Pythagorean identity there. So you have a couple options. You can write the next line on the left side, or you could even simplify 1 minus cos squared x to sine squared x. So it's your choice. I'm going to work on the right side. I'm just going to simplify that to sine squared x. And now we have left side equals right side. So we'll just finish up that proof. Okay, alternatively, you could have like exclusively worked on the right-hand side, and then you would have just done power of a power here using exponent laws, and then you would have got sine to the exponent 6. Oops, and I put an x here, so this should be alpha. Okay, make sure if you have a specific variable there that you're consistent with that variable, or otherwise just change them all to begin with so that you don't have multiple variables in there.